Hey, if you scroll down slightly further, there's a picture of me.
Use that as the beginning of this episode, please.
Welcome back to Coding with Qiskit. I'm your host, Jin. If you're new to this series, we cover topics in quantum algorithms each week, so be sure to like and subscribe. Today, we're going to be learning how to install Qiskit and use a very specific circuit library in order to build our first quantum algorithm. In order to access this library, we're going to have to install Qiskit locally first. So let's go through really quickly how to do this. So Qiskit is an open source SDK used for programming quantum computers using Python. And don't worry if your Python skills aren't there yet, we'll work through things slowly. So the first thing I'm going to do is navigate to qiskit.org. This will tell me exactly how to install Qiskit on my machine. And there's generally two options for running Qiskit. You can either run it on IBM's hosted Jupyter notebooks, or you can install it locally. And the first thing I want to do is, if I don't have Python installed yet, is to just install Anaconda, and this will install all the things I need for Python. Click download. I have a Mac, so I'll just do the 64-bit graphical installer and download. And like always, if you have a Windows or a Linux, just choose the appropriate downloader. Okay, so now that Anaconda has downloaded, I'll just open this up and I'll install. So what I'm going to do first is set up my Python environment, which just is a good way for me to organize my Python packages so that I have all the correct versions of all the packages in one place. So what I'll do is conda create -n, name of my environment, which will be coding with Qiskit or CWQ. I'll set my Python version equal to 3 and the Anaconda distribution. Okay, and I'm just gonna watch this little thing spin. Okay, now it's done. Okay, so I'm gonna proceed, yes. And now that thing's gonna spin some more. Okay, this might take a minute. So now that I have my environment set up, I'm gonna enter my environment by going to conda activate the name of my environment, which is coding with Qiskit. And I'm going to now install Qiskit into my environment. So from the qiskit.org site, just following these instructions, start locally. I'm going to choose the Qiskit stable installation. I have a Mac, so I'll choose Mac, but it's the same if you have Linux or Windows. Just choose the correct distribution. And then I'll copy this and pip install Qiskit into my environment. So now I have Qiskit installed, and I'm just going to open up a Jupyter notebook so we can get started with our algorithm. Perfect. So I'm going to open up a new Python 3 notebook, and let's get started with our algorithm. So let's build our first algorithm from the circuits library now. In order to do this, we need a few parts: some data to input, a circuit to run the calculation, and then an output. In physics, we often talk about signals, since signals represent the transmission of information. And generally, we use bases or units such as frequency or time to represent what kind of information that we're transmitting. I'm going to show you a quick example of an algorithm that's already built in Qiskit circuit library called the Fourier Checking circuit. The Fourier Checking circuit is an important tool used in the signal processing domain and is a fundamental circuit used in many other quantum algorithms, for example, Shor's algorithm, which we'll cover in a future episode. These circuits can be run on a real quantum backend or on one of the high-performance simulators that are available through Qiskit. All right, so let's get started with the algorithm. So the first thing I'm going to do is do my imports. So I'm going to import qiskit.quantuminfo as QI, and this is going to be doing the calculation. I'm going to import from the circuit library the Fourier Checking circuit. And I'm going to import my visualizer, Qiskit.visualization, import plot histogram. Okay, Shift Enter to execute that. So for this algorithm, I'm going to define two functions. They're just lists. F is equal to 1, minus 1, minus 1, minus 1. And G is equal to 1, 1, minus 1, minus 1. So now that we have our two functions f and g, the Fourier checking circuit will tell us how correlated the Fourier transform of g is to our function f. And it turns out that a quantum computer can perform this calculation much faster than a classical computer can. So the circuit will output a probability for the 0, 0 state. And if the probability is greater than 0.05, then the Fourier transform of our function g is correlated with our function f. Okay, so I'm gonna set up my circuit equals Fourier checking, and I'll put in my two functions, f is equal to f and g is equal to g. Okay, do circ.draw, see what this looks like. Okay, and this is what my quantum circuit will actually look like. So let's run this. 0 equals qi.state vector from label 0, 0. I'm going to evolve this. State vector is equal to 0.evolve my circuit. And I'm going to get my probabilities back here. Probs equals sv.probabilities. Probabilities. Okay, and then I'm gonna plot what this looks like. And remember, I'm only interested in the 0, 0 probability. Okay, perfect. So I get back a histogram here, and I'm only interested in the 0, 0 probabilities, which I get 0.25. So what this means is the Fourier transform of my g function is correlated with my f function. So you can try the circuit yourself and see how the outputs change depending on your input functions. This is where we'll stop for today, but hopefully now you have Qiskit installed, you're familiar with the circuit library, and you're able to run your first quantum algorithm. Make sure to like and subscribe because next time we're going to be talking about what it actually means to be a slower algorithm and why certain algorithms are better for quantum computers versus classical computers. Jin out! Can you just have a jump cut where I like teleport away?
Absolutely.